So, hello everyone. I'll just going to reintroduce myself because I forgot to start the recording. So, I am Kaustav Mukherjee. I am a PhD student in my final year at ISER Bhopal, and I am a PMRA fellow. And as a teaching requirement of my PMRA fellowship, okay, people still coming in. So, as a teaching requirement of my PMRA fellowship, I am taking a tutorial classes for advanced quantum mechanics course that is taken by Saurabh sir from IIT Guwahati. And today we are going to solve some of the questions that is relevant for or helpful for you in solving the week 1 of the assignment. So I'll share the screen. If you have any questions, you can just still coming in, people. Okay. And if you have any questions, you can just type in the chat box and I'll try to answer them. So I'll begin with sharing my screen. Okay, title notebook. So I believe you can see my screen. Okay, that's great. So let's start here. Advanced quantum mechanics course, week 1 tutorial. So sorry, I had prepared some notes, but because of some technical issue I'm not able to access them right now. So the first question that I'm planning to solve here is a potential will, that is a modified potential will. So let's say we have a potential. So this is similar to the question number 7, I think, in the assignment of week 1, but it's modified so that I'm not really giving you the solution, but I'm just going to show how you can solve such a problem. So what I'm taking here is v0 0 infinity for x less than 0, for x 0, sorry, x 0 x a, and for k, sorry. Does anyone know how do I make it such that everyone can enter without my permission? Because I have to click it every time and that will distract me a bit. People, whose controls still coming. Okay, I'm not sure how to do that. Fine, I'll just do what we can do here. Right, so getting back to it, x greater than a. Now this potential looks like you have an infinite potential, so let's just draw the axis first. Okay, this is v of x. We have, this is x equal to 0, this is the x-axis, and we have at a there is an infinite potential, so we make a infinite here, and for x less than 0 we have a potential v0. So let's say this is the width v0. Okay, and what we are going to do is we are going to check the boundary conditions here, and also we are going to find out the wave functions using those boundary conditions. So the basic at quantum mechanics or even in classical mechanics, we know that there can't be anything where wave function, there can't be any wave function where the potential is infinite, because the wave function cannot penetrate through the wall, right? And even if there is some definite potential, let's say v0 is a definite potential, and you have a ball, you need more energy, that's the E should be greater than v0 to cross the barrier. So let's say, for example, here we take the energy to be less than v0. Okay, that means it can't really penetrate. In classical sense, it can't, but as we learn from quantum mechanics, that you might have seen in your quantum mechanics previous courses, that there is a finite possibility or probability of the particle to be in this side where the potential is higher, even though the energy is less, and that's something what we call as quantum tunneling. But here I'm just going to show how these boundary condition we are going to figure out. Okay, now first thing is, at A we have a infinite potential, right? So that means psi, let's say we have three regions here. I'll mark it with 1, 2 and 3. So we have basically psi 1 at x less than 0, psi 2 at x from 0 to a, and psi 3 for at x greater than a. Now since at x greater than a the potential is infinite, that means there is psi 3 at a is supposed to be 0, as well as psi 2. Wait, sorry, there has to be some way to admit everyone. Alright, and psi 2 at a equal to 0. So the main boundary conditions that we always consider is that in quantum mechanics a wave function should always be continuous throughout the region from minus infinity to plus infinity, and the derivative of wave function is also should be continuous whenever the potential is finite, right? So here at a we have the condition psi 3 of a should be equal to psi 2 of a, and at x equal to 0, where there is also a step function that I have shown here, this region, there we have two conditions to be met, that is psi 1 of 0 should be equal to psi 2 of 0, that is the first continuity principle, and the derivative of psi 1 at 0 should also be equal to psi 2 of 0. Okay, this is right. So you can say these are the boundary conditions that we need to satisfy. Okay, so this is comes from the basic principles of quantum mechanics, that a wave function is supposed to be continuous everywhere and its derivative should also be continuous. So whenever there is a step, we have to make sure that it is continuous on either sides or at that point, right? Now once we have this, so we have the boundary condition now. Now I should add a page. Right. Sorry. Now next up is we are going to find the wave function. So to find the wave function, what we do is we use the Schrodinger equation, right? So we all are familiar with the Schrodinger equation, I hope. If someone's not, then they can tell. But I am hoping that everyone knows what is the Schrodinger equation. Now, solving a Schrodinger equation, we know that the basic is essentially we are going to solve is h psi equal to E psi, where h is the Hamiltonian, E is the eigenvalue corresponding to that Hamiltonian. Now here we have the potential that I have shown here, so I should write the corresponding Hamiltonian for this potential, right? So in any case, the Hamiltonian is always written as minus p square by 2m, which gives us the kinetic energy So this part gives us the kinetic energy, and there is a potential that I have defined in the first at the beginning, right? Now, so as I said, there are three regions, so we are going to solve for each region, except for the last part where the psi is 0 anyway. So for the first region, that is x less than 0, what we had here is that there is a potential V naught, okay, in this region. In this region, we have a potential V naught. So our Hamiltonian becomes H equal to minus P square by 2m plus V naught. That is a constant finite potential. Now, in order to solve this, what we do is we have the Schrodinger equation, that is H psi equal to E psi, and E is the energy of the particle. Now, so this is psi of x we have. Now, if okay, sorry, I missed a square here, sorry about that. Now, also we know the momentum operator is defined as P is equals to minus I h bar del by del x, that is a partial derivative of x. So putting this here, what we get is h will be minus I is it so? Sorry about that then. I have to check. Yeah, I also think so, it's minus. I will need to check once, but if you are convinced that it's plus. Momentum operator. So there is no Wi-Fi. It's fine. So okay, small tool. Okay, so as far as I remember, it's minus, but I am not really able to confirm it right now, but I don't think that will make much of a difference. So we have minus I h bar, let's say if minus is correct, so minus I h bar del by del x. People are still coming in, sorry about that, I have to discontinue in between. Minus I h bar del by del x square plus V naught, and this operates on the wave function psi of x, and we get E psi of x. Now this, if you put all the things together, so we have I square, which is essentially minus 1, and this minus does not really matter because minus square is always a plus. So what we have essentially is a double derivative, and there is h bar square, there is also 2m. Yes, so this is what we get from a free particle. So when you have a free particle, let's say there is no potential, okay, now for a free particle, you know that what you call as energy is given by your what do you say, your momentum is P equal to mv. This is classical, right? You know your momentum is given by mass into velocity, right? And you know that kinetic energy, so when you don't have any potential, that means the particle is free and it only has kinetic energy. Now kinetic energy is given by half of mv square, right? Now right, right. So what's your question again? So you were asking why we take p square by 2m, right? uh, is that so? Okay, maybe you're right. I am not good with minus and plus signs, so I'm sorry about that if it's so. Okay, right. Yeah, you're correct. Thanks for correcting me. So yeah, so from the I square we get a minus, so we get minus h bar square by 2m and the double derivative of psi of x plus v naught psi of x equal to e psi of x. So I'll just erase this part. Now most of you might have read about the how to solve a double derivative, and in order to solve it, we what we usually do is we take the parts that has a derivative to one side and all the others to the other side. So essentially we have a del x square psi of x equal to e minus v naught, and we get these coefficients to the other side, minus psi of x. Okay, now a general double derivative or a nonlinear differential equation has something like, if you write in this form, d squared equal to a square psi, where a is some positive number, then what you have essentially is d square minus a square. This is what you might have already read about in mathematical physics course. So you solve the d square minus a square equal to 0, and you get d equal to plus minus a, and the generic solution is psi equal to a e to the power I, sorry, here it should be ax plus b e to the power minus ax. So this is the generic solution for a differential equation which is of this form. Okay, so I'll just use that solution directly, and also we have already defined that v naught is greater than e, so I'll just going to write this as 2m by h bar square v naught minus e, and this becomes your the k square, you can say. Okay, so the general solution for psi x in the first region comes out to be a e to the power kx plus b e to the power minus kx. Now these a and b are the constants that we are going to find out through the boundary conditions. Okay, now in the second region, as this becomes more simpler because we don't have any potential, so it is essentially a free particle, and since e is greater than 0, so what we have, you might check from your books as well, that it's in the form of c cos, so let's say I give k1, c cos k2x plus d sin k2x. Because a greater than 0 and we have a minus sign, so it comes in the form of e to the power I kx plus b to the power I minus I kx, and you can change it because you have e to the power I kx in the form of sine or cosine. Okay, so this is the wave function that we have obtained. Now using the boundary condition, okay, sorry about this, using the boundary conditions that we have obtained, that first of all we have psi 3a equal to psi 2a, and then we have psi 1 0 equal to psi 2 0, and derivative of psi 1 0 equal to derivative of psi 2 at 0. There is something wrong with this. So I'll just use that. So let's say at x equal to 0, we first have the psi 1 of 0 should be equal to psi 2 of 0. Now that would mean that we have a some people come very late, it's okay. We have a plus b because we know e to the power 0 is 1, and on the right hand side we have only c. because sine of 0 is 0. So this is the first condition that we have obtained. So we are trying to find out a simple coefficient that can give us the throughout all the wave function throughout. Okay, now putting in the second one, that is derivative of psi 1 0 should be equal to derivative of psi 2 of 0. Okay, so the derivative of psi 1 is a k1 e to the power k1x plus b minus b k1 e to the power minus k1x. So this is at x equal to 0 supposed to be, and on the right hand side we have cosine and sine, right? So this is c k2 derivative of cos will be minus sine k2 of x plus d k2 cos k2 of x at x equal to 0. So what we end up with is a k1 minus b k1 equal to d k2. So these are the two, and then finally we have psi 2 at a should be equal to 0, which is also the psi 3, which is essentially 0. So at a we can write c sine k2 of a plus d k2. Sorry about this. I have missed one more boundary condition, that is at infinity the wave function should be 0, at minus infinity as well as plus infinity. So here we don't need to worry about plus infinity because at x equal to a itself the wave function is getting 0, but at minus infinity it should be 0. So we are going to use that one as well. Now here we have cos k2 of a equal to 0. So this is the third, and finally using that psi, is it so something's really wrong with this. Right, sorry. And finally we have at psi minus infinity the wave function should be 0. That's also one of the fundamental rule for the quantum mechanics. And psi at minus infinity is what we have, a to the power e k1 x plus b to the power minus e k1 x. So which one of these will be 0 at infinity by itself? Can you say? Can someone tell? So we have e to the power k1x and e to the power minus k1x. There are two terms here, right? Now which one of these terms will be 0 at minus infinity? Right, so this term will be 0 at minus infinity, right? So that means this b will be made 0. So from this boundary condition what we obtain is b should be equal to 0, and we only have a psi 1 of x is only a to the power k1 x. So what we obtain now, since b is 0, that means c is equals to a, and we don't really get much from this. So right, C is equals to A, and we need to find D in terms of A. Well, sometimes you can actually write in terms of the coefficients as well. If so, you can either put this term as 0 or this 0, because they can both be 0 at different a's, right? So this sign can be 0 at k2a equal to n pi, whereas cos k2a can be 0 at k2a equal to 2n plus 1 pi by 2. So both these, you can use any of these, because there is not a given wave function that you have to consider for any case. Okay, people still coming in, right? So through this, yes, so that is by itself 0, because we have the potential as infinity at x equal to a. So that means beyond x equal to a, anything is 0. So wave function is always 0, and we are not actually calculating the wave function in the third region because it's already 0. Yeah. Okay, so I'll then move on to the next question. Okay. Wait. Something else. Yes, sure. So for C and D, what I meant was that you have the boundary condition that C cos k2a plus D sin k2a equal to 0. Now, in case like this, there are not just a single solution. There is no unique solution. There can be any number of infinite solution. So if you can put the sin k2a as 0, and you can find the C, or you can put cos k2a equal to 0 and find the D. And in each of the case, you can have these conditions that you can put, that I am marking in the box, to get the relevant solution that you want. So in such cases, you don't have a unique wave function. There can be different coefficients for these cases. But in some examples where you have, let's say, when you have an infinite potential, okay, so in case of infinite potential, on both sides you have 0 wave function on either side. So at 0 it's 0, at a it's 0, and then you end up with something like sine n pi x pi a, something of that sort, coefficients with some root over coefficients. So the wave function is definite because there is only a single unique solution here. But when you have different number of coefficients, it's possible to have not a single unique solution, but a different multiple number of solution for the same case. So is that understood? Okay. Yes. So yeah, we have found A, and this A, what you can do is you can normalize the wave function and find out the coefficient. But in this case, you can't really do the normalization, because there are some cases where you have, let's say, e to the power I kx, that is a plane wave, and plane wave usually goes till infinity. So in some cases the normalization is not possible, but in most cases, when you have the finite set potential or this infinite potential box, harmonic oscillator cases, in those cases you can always find this A through the normalization. So normalization means that the psi square should be okay. So this condition is the normalization condition that is supposed to be satisfied. In most of the cases, the wave function is normalized. So whenever you calculate a wave function in any harmonic oscillator or this infinite potential box, in those cases these wave function are always normalized. But when you have something like a free particle, so the free particle can go from minus infinity to plus infinity, no one is stopping it. So the wave function being 0 at minus infinity or plus infinity does not make sense there, and in those cases the wave function are not normalizable. So is that clear? Yes. Right. Yes, yes, yes. Right. So if you have, you can go to the Fourier. Of course, Fourier space is much helpful in those cases, but in a normal sense, like let's say you are just beginning at the quantum mechanics, and you have a wave function that is a e to the power I k x. So in Fourier space, you know that it goes to a delta function type thing, but in this in the position space, it's not really normalizable because you don't have it. You can't make it 0 at minus infinity or plus infinity. The wave function remains. So in the position space, it is not possible to normalize such a wave function. Yes, yes, sure. Okay, so first thing is you can't really imagine it, the Fourier space, but in cases like I can't really think it just right out of my mind, but it does have a lot of information that you can obtain from the Fourier space. Like let's say there is a combination of plane waves, okay, and it's often difficult to distinguish between the different frequencies of these combination of plane waves. So what you do is you Fourier transform it and you get definite frequencies, you get sharp peaks at definite frequencies. So that basically does a Fourier decomposition of the combination of the plane waves, and it gives you a lot of information that you need. Okay, just a second. Yeah, so that gives us a lot of information that we need regarding the frequencies. So often you don't have a single or monochromatic laser in experiments. Okay, now if you are shining a laser with a wide range of frequencies, then what you don't really have the idea what is happening actually in the system. And to understand which frequency is actually doing anything in the system, you need to know the Fourier transform of these, and you get the range of frequencies that is impacting on it. And finally you will see that there is one frequency that is missing, and that frequency is actually absorbed by the system or some gas. You can have iodine gas or sodium gas, and you when you shine the laser, then you will see that there are some particular frequency missing, and that is only possible when you know the Fourier of this spectrum. So that's how I can think of and like directly, but there are other applications as well. You can put the question on the forum and I'll try to think of more examples to put it on there. So this was roughly clear, right? How? Yeah, okay. So the next question is something simpler was there. Yes. So this question actually corresponds to, I think, the last question of the assignment. So let's say we have a hydrogen atom and we have the electron in the first excited state. So I'm not actually solving the question of the assignment. Assignment, you have been asked to solve for second excited state, that is n equal to 3, and I'm just going to show for n equal to 2, then you can easily manage to do for n equal to 3. So the first part was to find out the energy of the electron. For some of you it might be very easy, and I'm not sure if it's actually any difficulty in solving this. So for hydrogen atom, we know that the electron energy, the energy of each state, is given by minus 13.6 by n square ev. So this formula I think everyone is very familiar with. So in order to find the energy for the second excited state, we put n equal to 2 here, that I have already written over there. So the ground state is n equal to 1, and then we have the second excited state at 2, 3, 4. Okay. So for n equal to 2, what we have is minus 13.6 by 4, which is minus 3.4 eV. So this is pretty straightforward. And sorry, there are more people coming in. Okay. Then is a bit trickier question, that you have to find the number of wave functions corresponding to the first excited state. So for ground state, we know that n is if n equal to 1. So you know the range of L, that is the angular quantum number, goes from 0 to n minus 1. And then we have the m, which goes from minus L to L. You can correct me if I'm wrong at any point of time, because I'm at PhD final year and some of the initial stuffs are a bit loosening up. So like the minus signs, I have messed up a bit somewhere. So for this case, we know for ground state there is only one possibility, that is S00, that is the wave function. But for first excited state, and it goes a bit more complex for the second excited state, which you are going to calculate for your assignments. So in first excited state, we have n equal to 2. We have n equal to 2, and the L goes from 0 to 1, and for each L we have minus L to L. So the wave functions, the number of wave functions that we can get is psi 2 0 0, first of all, the S basic state. Then we have psi 2 1 0, psi 2 1 minus 1, and psi 2 1 1. So this is the L, this is M. So for L equal to 1, we can have M as 0, minus 1 and plus 1. So here we only get these 4 number of wave functions, and for n equal to 3, you will end up with a larger number of wave functions. Now for the C part, we have calculate the ionization energy. So I believe everyone knows what is ionization energy. It is the energy that is required to pull that electron out of that hydrogen atom. So if you have an electron in the first excited state, how much energy you need to just shoot it off the atom. So for that purpose, you need only the energy that is already that electron possesses. So if you put 3.4 electron volt in the plus, then the electron just shoots off. So essentially the ionization energy is only 3.4 eV. And in the final case, D, we have to frequency required to excite electron from ground state to first. Okay, that is also pretty straightforward. So the question is, if you shine a laser and you have an atom, the hydrogen atom, the electron is in the ground state, how much energy is required, or the frequency of the laser is required? Okay, so I think I've missed some. There were comments here. I'm sorry about these. Which book to reference syllabus? I think that's already mentioned in the course. R. Shankar, I think, is one of the preferred one. You can go for Griffiths, and there are many books you can refer to. The kinetic energy operator has a negative sign. Sorry about that if I messed it up. A coefficient, I don't understand that. And so what is S here? Subscript of psi. Oh, so this S is essentially, sorry about it. S is basically n equal to 1. So in our work we usually have n equal to 1 refers to sorry, that was supposed to be L equal to 0 for S. That was my mistake. So it's actually n equal to 1, nothing else. Okay, yeah, so where was I? D. Yeah, so the frequency nu required to excite electron from ground state to first excited state. So this is also a very straightforward question. You have the difference, you find out the difference between the two states, that is the first excited state. So this for first excited state minus for the ground state. And we have already obtained this part, minus 3.4 eV, and we have plus 13.6 eV, and this essentially gives us 10.2 eV. Now this is the energy of the laser that you need to excite from the ground state to the first excited state. So the frequency of this is given by h nu equal to 10.2 eV. So eV is 1.6 into 10 to the power minus 19 joules. H, you are all familiar with the Planck's constant. So this is 13 joule second, nu 10.2, and if you just solve it, you will get something like 2.46. It doesn't really matter what you get, you get something of this order. So this was a very straightforward question. Now come to the third question, which might be a bit more tricky. So this is actually relevant to the 0 point energy that that is asked in the assignment to be calculated from the uncertainty principle. But here I'm not going to show using the uncertainty principle, but I'm going to show it using your I'm just going to derive the ground state harmonic oscillator, and from there you can actually calculate the ground state energy. So ground state harmonic oscillator using the ladder operator. So are you all familiar with the ladder operators? There is no response. No. Okay, it's fine actually. Even if you not remember, I can just give you a brief intro to the ladder operators. So there are two ways to solve the harmonic oscillator. Okay, now there is one a purely analytical way to solve it, and there is a algebraic method that uses ladder operators to solve. So using ladder operators, you can actually find out the 0 point energy very easily. So what you have is in a ladder operator case, you have two operators, a plus minus, which is given in this form, 2h bar n omega. I'll just briefly write it and then explain what it actually does in principle. So minus plus ip. Now here this x is the position operator and p is your momentum operator. So what ladder operator essentially does is, if you have, so in algebraic method we have the harmonic oscillator states defined in the form n. Okay, so that means you are in you have n number of particles in one of the states. Is that right? Now if you use a plus operator from this, what it essentially does is increases or excites to a higher state, whereas if you have a minus operator, it reduces to a lower state, de-excites. So it's like you have a ladder. The A plus operator puts you from here to upper state, whereas A minus operator puts you to a lower state, that is the n minus 1 state. So what is one of the fundamental rule here is that the ground state, that is the 0, n equal to 0 is your ground state. So if you operate A minus on a ground state, you will always get 0 because you can't really go below the ground state. And Hamiltonian for these operators, you can go through the Griffith's book. Yes? Yes. So for you cannot go below the ground state. So in classical cases, you always have a 0 point energy that is given as the 0 of any potential. But in quantum mechanical, there is a finite energy of the harmonic oscillator, that is the 0 point energy. Now the Hamiltonian for these cases are given in the form A plus A minus plus half h bar omega. I think I missed this one. It's supposed to be minus plus. Okay. I'm just getting a bit confused here. So I'm sorry about this. I can be wrong. So what one does is, this is actually the number operator. I will have to check which sign comes first. And this number operator, probably think the minus comes first, but it's fine. This number operator essentially gives us the, if it's operated on n state, this gives us n. Now if you have this case, then what will have, if you have a minus sign here, so for when it's implemented on 0, it will give you a 0. And since the 0 point energy for state 0, because the ground state will be the giving the 0 point energy, this is from the Schrodinger equation, we have h psi equal to E psi, right? So this gives us the 0 point energy. So when you put n plus half h bar omega acting on 0, you have E naught 0, and from there you can easily calculate that n will be operating on 0, and that gives us a 0, and half remains as it is. So your 0 point energy essentially comes out to be half h bar omega, which you are supposed to calculate in your assignment using the uncertainty principle. So there you have to find the delta p, delta x, and you have to take the derivative. And if you want, I can give you some hints on how to solve it using the delta p and delta x, but this is the ultimate solution that you're supposed to get using the uncertainty principle. Okay. Yes. For nth energy, this basically comes out to be E naught equal to n plus half h bar omega, because when you are when you are operating on this n level, then you essentially get just n. So for the nth energy, you will end up with this kind of an expression, n plus half h bar omega. Yeah. Okay, so now I have some just basic questions. We are moving towards the end of this tutorial. If you have any further question, you can ask. If I'm able to answer it now, I'll try my best. Otherwise, you can put it on the forum and I'll try to answer your questions there. Now, one final question. is to find which one is a linear operator. So I hope you already are aware of the definition of linear operators. So a linear operator is defined in the form: if you have a operator O acting on a function a f of x plus b g of x, then you get a o f of x plus b o g of x. So this is how we define as a linear operator. So it means that if you have two different functions, then it should linearly add up. Okay, it cannot be in the form like a o f of x into b o g of x. So this is not right. It has to be in the linear. The way the function is defined, the linear operator should be acting as it is. Okay, so for example, we can take few examples here. Let's say we have the simplest example just for demonstration, and then we take a complex example to do a more complex scenario. We have, let's say, a psi 1 of x plus b psi 2 of x, where the operator is defined as derivative d by d of x. Okay, now here what we have essentially is the operator x d of x is acting on a psi 1 of x plus b psi 2 of x. So how this will be done? So when it's operate on the first term, we have x a d psi 1 of x by dx, and when it operates on the second term, we have x b d psi 2 of x by dx. And this essentially, if x and a commutes, because a is a constant here, so we can put a before and x after, and you can essentially write it in the form of psi 1 of x plus b o psi 2 of x. So this is just like as I've written here. This operator then corresponds to a linear operator. Now taking a bit different type of example, let's say we have x cube. O1 is defined as, let's say this is O2, and we defined it as x cube is fine. So what do you think from your first claims? Will this operator be a linear operator or a non-linear operator? If I implement this, if I put this operator on action on this wave function, what do you think? Will it be a linear operator or a non-linear operator? Non-linear operator. Okay, linear operator. Okay, this one is simple. Non-linear. Okay, so let's have a look. So when x operates on psi of x, it just gives us x psi of x. There is nothing special happening here, right? So if you have O2 operating on a psi 1 of x plus b psi 2 of x, so this essentially gives you a x cube psi 1 of x plus b x cube psi 2 of x, and which is essentially your O2 psi 1 of x plus b O2 psi 2 of x. So this is a linear operator. And let's say if we take O3, another example, to be e to the power x. sorry, let's say I define it as O3 psi of x. Let's say I write the psi of x here. So if you have O3 psi of x as e to the power psi of x, so what would your answer be? Will this be a linear operator or non-linear operator? Just a rough guess. You don't have to be correct. Non-linear, and I think that is actually the correct answer. So let's solve it and verify if it should be a non-linear or a linear operator. Okay, so we have a psi 1 of x plus b psi 2 of x, and what we have here is a naturally comes out, it's a constant. So O3 acting on psi 1 of x gives us e to the power, I think I'm doing something wrong. Right, so the O2 acts on the whole thing. Sorry about this, I was doing it a bit wrong. So this is supposed to be the operator acting on the whole thing plus b psi 2 of x, and then you take the derivative of individuals, and here also this is operating on the whole thing, otherwise it won't make sense. And then you have, when you put the multiply on x cube on each of them, then you get the same thing. So now this is the psi of x here. Okay, so this whole thing goes into the exponential. So we have a psi 1 of x plus b psi 2 of x. Now we know that these are not really, these are, the a is not here, sorry about that. Now we can write it in different way. So you know e to the power a plus b can be written in the form e to the power a into e to the power b. So this can be written as e to the power a psi 1 of x plus, we have e to the power b psi 2 of x. Okay, so essentially you can write it in this form. Yes. No, actually, so if you have, let's say, any operator, okay, so if operator is acting on a of f of x, so it's not like the thing, so if it is e to the power a of f of x, okay, so operator is acting on the whole thing, it's not just acting on f of x here. Do you understand the point? So this whole thing is a function, let's say g of x is defined as a f of x. So can you just take out the a? You can't, right? Even if a is not a function, if g of x is defined as a f of x, a is a constant. But if you are writing o g of x equal to e to the power g of x, and then you substitute this, what you will get is e a to the a f of x, right? Okay. Okay, so what we have here is essentially e to the power a, you can take out into e to the power, so what we have here is O3 acting on a psi 1 of x and multiplied by O3 acting on b psi 2 of x. So this is not in the form. So what should have been the form is O3a psi 1 of x plus O3b psi 2 of x for it to be a linear operator, but that's not the case here. So what we will say is this is a non-linear operator. So similarly you can take a lot of examples. There are endless number of examples here, and I would like to finish up with this one. If you need more examples, just to, because I got confused myself a bit, so it's possible that you also would have been confused, and if you want one more example, then I can do that for sure. Would you like that? Okay, I'll do one more example. Let's take this one. P. Okay, so we have O4 psi of x defined as lambda of psi x conjugate. So you are all familiar with conjugates, right? Conjugate is your complex. So if you have, let's say, complex number z equal to x plus iy, this x z star would mean x minus iy. Everywhere wherever there is an imaginary thing, that gets a minus sign. So I hope you are all familiar with it. Otherwise this is just the basic definition of whatever a conjugate is. If you have a complex number, the imaginary part gets a minus sign. Okay, so for this case, let's do the same procedure again. A psi 1 of x plus b psi 2 of x. Okay, now this operator, I'll just repeat, this operator will act on the whole thing. So we have psi of x here getting a psi x conjugate. So this whole thing will get a conjugate with a lambda sign. So what we have here is a psi 1 of x plus b psi 2 of x conjugate. Okay, now this conjugate individually conjugates each of them. Right. Yeah. So we have a conjugate psi 1 of x plus b conjugate psi 2 of x, and what we end up getting is a star lambda psi 1 of x plus b star lambda psi 2 of x. So for this part you can write it as operator O4 of psi 1 x, right? Because the definition is in this form. So if you have a psi of x, this is acting on psi of x, we get a additional lambda here and the psi star of x. So here also you can say, sorry, there were conjugates on this too. So here you can say that lambda psi 1 star of x is essentially the operator acting on psi 1 of x, and similarly here we have the operator acting on psi 2 of x. But this is actually a operating psi 1 of x, b star creating psi, sorry, O4 psi 2 of x. But are these the same? So would you call this a linear operator or non-linear operator? Right, because this is a conjugate. So let's say if a conjugate would have been a, which means if a would have been real and similarly b would have been real, then would you have called it a linear operator or non-linear operator? Then it's a linear operator, right? So I think now you have understood it perfectly. So if these are not real, then it's a non-linear operator. But if it would have been a real number, then it would be a linear operator. So I hope this is now clear to everyone. If you have any questions, you can ask, or we will just end this meeting. So I suppose there are no questions, and I would like to thank you all for joining this tutorial. I had great time with you all, and we'll see you next week. So have a good day. Take care. Thank you all. So I'll end this meeting. You can put the question on forum, and I think there are other tutors as well. We will put it there. Okay. Thank you.